All right. Well, I see my two favorite people. Can you hear me?
Yeah.
All right. Was Monday a Columbia holiday?
Yes, it was. Monday,
okay.
Tuesday. It's always been because of the election, so they'd go home and rabble rouse elsewhere was the original.
Right, exactly. I had forgotten that until I had a very low turnout yesterday. I mean, Monday. I couldn't tell if that was because I scared everyone off or all the Columbia people thought it was a break.
Did you miss anything? Did you stop or did you go on?
What did you say, Elliot?
I said I had forgotten it too, that it was a holiday.
Did you try to teach?
No, I don't teach Monday. I teach Tuesday, Thursday.
All right. So it didn't really matter to you.
No.
Do we have a lecture we should go watch the recording of?
Oh, I just posted it. It was not my finest performance. I got confused at the end. So I spent the first 2/3 of the talk just saying what Bott periodicity was. And then I started in on how you actually prove it using the loop space. So I'll recap that briefly at the beginning of this lecture, but mainly what I want to concentrate on is the proof using the path space. All right, well, I guess it's time to start. So this is Bott periodicity. Part 2. So the main technical result in Bott periodicity is that there's an embedding of the Grassmannian of complex n-planes in 2n space inside the loop space of SU2n as the space of minimal geodesics. And this, so it is the, it's a Bott-Morse submanifold of critical points, and all other critical points have index greater than or equal, in fact, it's twice n+1. Okay, so that's the statement. It follows from this statement and the generalities of Morse theory that pi I of this Grassmannian to pi I of the loop space of SU2n. Up here, I'm talking about actually not the loop space, but the path space of paths that go from E to -E. But here I'm talking about the actual loop space. These spaces have the same homotopy groups. This is an isomorphism for I less than or equal to n, because you get the loop space by adding handles of index at least 2n+2 to this minimal set, the Grassmannian. So adding those handles will not affect the homotopy groups in dimensions 2n or less. And then you take limits and you see this thing limits to the classifying space for the unitary group, and this thing limits to the loop space of the infinite special unitary group. And this becomes a homotopy equivalence, an isomorphism by the stability result, an isomorphism on all homotopy groups. That's Bott periodicity. It's an incredible theorem, and we see periodicity by looping this homotopy equivalence. If you take the loop space on BU, you get something homotopy equivalent to the second loops of the special unitary group. But by the general theory, if you take a Lie group and you take its classifying space and then you loop it down, you get back to the unitary group. So you see that the unitary group is homotopy equivalent to the second loop space of the special unitary group. And as a consequence, for example, pi I of the unitary group is Z when I is odd, greater than 0, and 0 for I even. So the homotopy groups of the unitary group form a periodic sequence of period 2. That's another form of Bott periodicity. So I think I undersold this theorem last time, so let me just give you my impression of this theorem. The idea that you could have a space, a naturally occurring geometric space that satisfied this kind of periodicity was just unheard of. If you took a small space like a compact manifold and looped it, you got an infinite dimensional space with homotopy groups in arbitrarily high dimensions. You never expected some repeated loop space to bring you back where you started. Of course, this isn't a finite dimensional manifold, it's a limit of finite dimensional manifolds. Nevertheless, that you have a naturally occurring geometric space so that you could compute all its homotopy groups, and they satisfied this simple pattern. It was never even conceived of. Once we knew how complicated the homotopy groups of spheres was, we just never thought you were going to see spaces. I mean, you can make by hand in homotopy theory spaces that have these kind of properties, but a naturally appearing geometric space, no one ever even conceived that such a thing could be true. And of course, it has incredible consequences in K-theory, topological K-theory. As far as I'm concerned, this is the best theorem ever proved by somebody under 40 for which a Fields Medal wasn't awarded. So it came down in the end, the last Fields Medal, the others had already been decided, was between Milner for exotic structures on spheres, I guess, and Bott for periodicity. And it went to Milner, who could have won it later. He wasn't that old, but Bott, that was Bott's last chance. So he got frozen out. Anyway, okay. So remember, we're using the inner product on the special unitary group. The Lie algebra is simply minus trace AB. And this is a positive definite, a bi-invariant inner product. And you push it around to give a Riemannian metric by left multiplication. So using, it doesn't really matter since it's bi-invariant, but using left multiplication, we get a Riemannian metric on the Lie group, which in fact is a bi-invariant Riemannian metric, invariant under both left and right multiplication. Okay, last time we saw that the geodesics, well, any geodesic is conjugate under the conjugation action of SU2N to a geodesic of this form, e to the I A1T e to the I A2NT 0, 0. So diagonal matrices of that form with the AI real. That's because the tangent vectors at the origin are skew Hermitian matrices. So I times them are Hermitian matrices, and Hermitian matrices can always be self-adjoint Hermitian matrices can always be diagonalized, and they have real eigenvalues. So when you take the derivative of this thing at the origin, you get purely, up to conjugation, you get purely imaginary entries down the diagonal. And then so that's a tangent vector. Now when you integrate it, exponentiate it. When you exponentiate a diagonal matrix, you get a diagonal matrix. So that's what the geodesics look like up to conjugation. To be an SUN, I need summation of these AI to be 0. That's the trace condition on the derivative or the product condition on this expression. Okay. Now I want paths from the identity to minus the identity. So then we need, well, these are geodesics starting at the identity. You set it t equal to 0, you get the identity matrix. I need them to be the minus the identity at t equals 1. So I need e to the I aj times 1 to be minus 1, which means that aj is pi times nj, where nj is an odd integer. Okay. And I'm going to change notation now and call these geodesics e to the I pi n1, e to the I pi n2n. Sorry about the n's. It doubled. Maybe I'll write this a little bigger so that you can see it. So our geodesics look like, geodesic paths look like e to the pi I n1, e to the I pi n2n, diagonal matrices. The ni are odd integers. Okay. So those are the geodesics, and now the extra condition is the summation of the ni has to be 0. And what's the length of this geodesic? Well, let's take the derivative at the origin of this geodesic. That's the matrix I pi n1, I pi n2n. So when I take minus trace gamma dot squared, I simply get summation minus pi minus summation minus pi ni squared. So I get summation pi ni squared, I equals 1 to 2n. That's the square of the length. I mean, that's the square of the norm of the tangent vector. So the length, tangent vector has a constant length, is simply the square root of this. So it's pi times the square root of 2, pi times the square root of summation ni squared. Okay. So the minimal geodesics are when ni is plus or minus 1 for every I, and they're exactly n plus 1s and n minus 1s. You need n plus 1s, and if you're going to use all ni equal to 1 in absolute value to satisfy the SUN condition, you need half of them to be plus 1 and the other half to be minus 1. And these minimal geodesics are of length pi square root 2n. Okay. Every other geodesic is longer. Okay. Well, associated to such a geodesic gamma, we associate an n-plane, a complex n-plane in C2n, namely the I pi eigenspace. Remember, our geodesic wasn't of this form. It was simply conjugate to an element of this form under the special unitary group. So I have half the ni are positive and half are negative. So I get 2 perpendicular eigenspaces, and they're both planes, perpendicular planes of dimension n, complex planes, NCN. I choose to use the positive one. So gamma then corresponds to a point in the Grassmannian of n planes in 2n space. And clearly, given any point in the Grassmannian, there's a special unitary isomorphism that carries that plane back to the standard plane. And then if you conjugate this by the inverse element, you'll get a geodesic that has the given plane as its eigenspace. So the minimal geodesics are identified with the space of minimal geodesics are identified with this Grassmannian. Complex Grassmannian of n planes into n space. If you calculate its dimension, its complex dimension of this Grassmannian is n squared, and therefore its real dimension is 2n squared. So we have a manifold, a real manifold of real dimension 2n squared, which is this family of minimal geodesics. Okay. And the theorem, just to state it now, is that this Grassmannian of minimal geodesics, 2n, is Bott-Morse, and every other geodesic as index greater than or equal twice n plus 1. Okay, that's what I said before. All right. So we have to compute two things. We have to compute the kernel of the Hessian at a minimal geodesic and show it has dimension 2n squared. And we have to show all other critical points have negative space of the Hessian at least twice n plus 1. Okay. And for that, we're going to use the following general theorem about indices and critical points. So suppose I have a geodesic, and this is quite general. It can be in any manifold, Riemannian manifold, geodesic. For each t in 0, 1, let jt gamma be the subspace of Jacobi fields along gamma that vanish at 0 and at t. They're allowed to vanish other places too, but they're required to vanish at these 2 points. Okay. Then the theorem says 1, jt gamma is finite dimensional for all t. 2, jt gamma is the 0 vector space except for finitely many t. And 3, the index of the Hessian at gamma of the energy functional is the sum over t between 0 and 1, but not 1, of the dimension of j, t, and gamma. Okay. So what happens is, draw some eigenvalues in spectral flow. So here's 0, and here's a bunch of eigenvalues that E has. Starts off, the Hessian is positive definite for sufficiently small time, so all the eigenvalues are positive. Then as you move out along the curve, so this is the length of the curve, the t direction, or the t parameter, these eigenvalues start moving around continuously. And at some point, one or more of them may hit the origin and cross. This happens when JT gamma is not equal 0. Well, that makes sense because this is the condition that if you restrict to the interval 0t, you have a kernel, because now you have a Jacobi field vanishing at both endpoints of this subinterval. So suddenly your Hessian has a kernel, which is the only way eigenvalues can pass from positive to negative. And what this theorem says, among other things, is once you come to a time when this Jacobian is negative, all the eigenvalues, however many they are, all cross over and become negative. So they cross 0. So you go a little bit later in the next t where the kernel is 0 and you have some more crossing. Now you could imagine that some of the negative eigenvalues come up and cross back positive. In general, that will happen for a general one parameter family of operators like this, but that never happens here. The eigenvalues below 0 stay below 0, and you only add more to them. And so what happens is the only time you add eigenvalues in the negative part are when you cross these t for which jt is non-zero, and then all the eigenvalues associated with that space cross over to the negative. None of them ever come back, and so this is the index of the Hessian. And of course, the kernel is the dimension of j sub 1. So when t equals 1, these Jacobi fields now vanishing at the two endpoints don't give negative eigenvalues, they give the 0 eigenvalue. So that's the picture. I'm not going to prove this theorem. It's a beautiful argument, but it would take us too far afield. You can look in Milner's book if you want to see a version of the proof. Anyway, I'm going to use that theorem. Okay. So this is where I got bollocksed up yesterday. The argument now proceeds in two steps. One, we have some general theory for Riemannian symmetric spaces. And then we have two, a computation using that general theory for SU to N. And all of this is aimed toward understanding the Jacobi equation on these manifolds. So the general theory is what the Jacobi equation on a general symmetric space looks like, and then applying that general theory to the special unitary group, you get a very beautiful picture. Okay, so remember, as I defined it last time, a symmetric space has the property for every point P, there is an isometry TP that stabilizes every geodesic through P, but reverses its direction. Or so TP is an isometry, and the differential at P of TP is minus the identity. So it's an isometry. It sends geodesics to geodesics. If it flips the tangent space by -1, it has to flip the geodesics over. That's the definition of a local symmetric space. If you have 2 points on a geodesic P and Q, where this is gamma of 0 and this is gamma of A, say parameterized by arc length, then if you do the reflection in P followed by the reflection in Q, it takes gamma of T to gamma of T plus 2A, exactly as if this were a straight line and this was the usual reflection in 0 and reflection in A. It would make a translation of size 2A, translation of size 2A. And of course, that's an isometry. Okay. So now we want to apply this in the following situation. Suppose gamma is a geodesic and W and V are vector fields along gamma parallel along gamma. Then the Riemannian curvature of WV, remember that's an operator on the tangent space. You can apply it to V. So this is a family of operators on a tangent, on the tangent space. This is a parallel. This is, sorry, parallel along gamma. So the action of this curvature operator applied to WV, the curvature operator using WV applied to V, W and V being parallel, gives you a new parallel field. And the proof is, suffices to show clearly, that for all X parallel along gamma, the inner product is constant function of t as you move along the curve. Okay, because the inner product is also parallel. Okay, well, let's take one of these t, which is TQ TP. So t of gamma t is gamma t plus 2a, and t is an isometry. If it's an isometry, it, well, so the first thing to notice is that t of w at t of w at t is w at t plus 2a. And similarly for v and x. So in other words, if you have a parallel vector field and you apply this isometry, which shifts you down the curve, it takes the parallel vector field to itself, shifted down the curve. So that's the claim. And the proof of that claim is simply TP of WP is minus WP. Because, so this is just the value of this parallel vector field at P, T, so it's an element in the tangent space at P, and TP acts on the tangent space by -1. But that implies, since W is parallel, it's completely determined by its value at any point. So that implies TP of the whole vector field is the negative. And of course, that has to be interpreted as TP of W at T is minus W at minus T. Okay, assuming P is P is 0. Well, the same argument works for Q. So we see that T of W at T is equal to W at T plus 2A. And similarly for V and X. And now you just look at this expression, apply T to it. I get the same expression again, but I've shifted down the curve by 2A units. That says this thing is a periodic function with period 2A, but A was arbitrary. So that implies the result that this R, W, V, X is constant, since this is true for every A. Okay. All right. So what happens now is you take R, V, W, which is a map from the tangent space at, this is at some point P, of the manifold to the tangent space to the manifold. This turns out to be self-adjoint. This is a basic fact about the Riemannian curvature. you can actually think of the Riemannian curvature as a symmetric map from wedge 2 of the tangent space to wedge 2 of the tangent space. Okay. In other words, the symmetries are RVW. RWV is minus RVW. Skew symmetry in the first two variables. RWVAB is minus RVWVBA. So if you switch the first two variables, you introduce a sign. If you switch the third and fourth variables, you introduce a sign. And if you switch the pairs, RWVAB equals RABWV. So if I switch the pairs, keeping the order, the relative order the same, WV and AB, I get the same answer. And using these, you prove sort of a direct computation. This is self-adjoint. So that means this operator diagonalizes by some orthonormal basis, W1 up to Wn. So there's an orthonormal basis in which this thing is diagonal with A1 up to AN, if n is the dimension of the manifold, down the diagonal. Okay, just the spectral theorem for finite dimensional self-adjoint operators. Let me call them actually not A, let me call them E. Okay, and now what's the Jacobi equation for something of the form AI of T EI WI? Okay, so an arbitrary vector in this vector space is a linear combination of the WI, and now, so these things, we parallel translate them. So WI is the parallel translate of little wi. So that forms a basis at every tangent space along the curve, and an arbitrary vector will be then a linear combination depending on T of these basis vectors. And the Jacobi equation, remember, says that the covariant derivative in the T direction twice of W plus the Riemannian curvature of W on gamma dot applied to gamma dot equals 0. Okay. Well, this isn't. So what we know is that R of WI gamma dot is EI WI. That's the statement that, well, at the origin, that these form an orthonormal basis and these are the eigenvalues. So this is the operator. It sends this variable to the answer. And these are eigenvalues. And now, because this thing is parallel, the same equation holds not only at the origin, but it holds for this parallel vector field W, because I have two parallel vector fields and they agree at the origin. Okay. And of course, since the WI are parallel, we know how to take covariant derivatives. It's just the ordinary derivative of the AI. So the Jacobi equation becomes AI double dot of T WI plus EI WI equals 0 for all I. So in a symmetric space, the Jacobi fields split into these one-dimensional spaces given by the eigenvalue, by the eigenspaces of this operator. And along that one-dimensional space, you just have, you know what the solution looks like. So a solution, say in the I space, would look like sine square root EI T, and with a constant out front. Because this is a field that vanishes at the origin. It solves this second order equation with eigenvalue here, EI, well, and this would be times WI. Okay, so that's the Jacobi fields preserve this decomposition, this parallel decomposition. So it's a collection of one-dimensional equations, and the one-dimensional equations are just signs with the square root of the eigenvalue there. Okay, so that's the general theory of the symmetric spaces. Now I want to apply this to the unitary group. So now we're going to apply this to SU2N. Remember, our inner product was at the origin minus trace AB. Okay. And our geodesics, well, up to conjugation, I can always assume they're diagonal. So the geodesics look like e to the I pi in 1, e to the I pi in 2n 0, 0, summation of the ni equals 0. That's my geodesic. Okay. And the tangent vector is, of course, the diagonal matrix I pi n1, I pi n2n at the origin. So I need to understand the decomposition of the operator R W gamma dot at the origin, gamma dot at the origin. So that's a map from the tangent space at the origin. That's a map from the Lie algebra, SU2N to SU2N, symmetric with respect to that inner product, self-adjoint with respect to that inner product. And I have to figure out what it looks like. Well, here's a little lemma in any compact Lie group, that if X and Y are left invariant vector fields, then covariant derivative in the X direction of Y is 1/2 the bracket of X and Y, bracket of vector fields. Okay. I'm a little short on time, so I don't think I'll prove that. Maybe I'll just sketch the idea. Proof, you first show for a left invariant vector field that the covariant derivative of X in the X direction is 0, which just says that the tangent vector to the geodesic is left invariant gamma t times gamma dot of 0. So the covariant derivative of gamma dot of 0 in the gamma dot direction is the derivative of this thing, which is trivial. Covariant derivative of this thing, which is trivial. Anyway, then you apply that to X plus Y of X plus Y. The XX and YY terms vanish, so you get, and this is 0 because X plus Y is left invariant. And you also have the torsion equation, torsion-free equation, which says this is the bracket. You add these two equations and you get the result. So that's a brief indication. It's completely standard limit. Okay, so now I need to compute R W V on V. There's an operator in W, so V is fixed. Well, this is covariant W, covariant V of V, minus covariant V, covariant W of V, minus covariant of the bracket of WV with V. That's the definition of Riemannian curvature. If W and V are parts or the coordinate derivatives in a coordinate system, then you don't have this term and you just have the usual cross partials difference, which won't vanish. That's what curvature is about. If you take general vector fields to have a tensor, you have to put in this covariant derivative with respect to the bracket. All right, well, this is the covariant derivative of 1/2 V bracket V. That term vanishes, V bracket V is 0, minus the covariant derivative of V of 1/2 W bracket V, minus 1/2 the bracket of W with V applied to V. Okay, now I do this one, so I get minus 1/4 V WV minus 1/2 WV V. But notice these two are brackets in the opposite order. So you switch the order of this one, you make the sign +1, and so this all adds up to 1/4 V W V. Okay, so that's RWV of V. So that's the operator. Okay, so now for V, a diagonal matrix, I pi A1, I pi A to N. Conjugation by V on a vector, a matrix with only one one non-zero entry gives you, too many I's here, I pi AI minus I pi AJ times EIJ. So in SUN, for each IJ, for each I less than J, you have a two-dimensional, one complex dimension, or two real dimensional eigenspace with eigenvalue I pi times AI minus AJ. That's the matrices, skew Hermitian matrices with EIJ and multiple times EIJ and the conjugate minus the conjugate times EJI. Okay. So now if we take 1/4 VWV, well, that's minus 1/4 VW. And so these so we get the same eigenspaces, but the eigenvalue is minus the square. So EIJ gives an eigenspace, two-dimensional eigenspace with value lambda equals minus 1/4 I pi sorry, I don't want to do that. Let me just say what the answer is, because I screwed up the computation a little bit. I didn't want to switch these two. WV. So you get an eigenspace with eigenvalue pi squared AI minus AJ squared. So the i's, when you do this operator twice, you get a sign from the I squared, but you also get a sign from reversing the order of the action here. So the whole thing is positive. So this is a two-dimensional 2D eigenspace with lambda ij equals pi squared, well, over 4 because of the 1/4, ai minus aj squared. All right, so those are the off-diagonal entries. The diagonal entries commute with the matrix, so they're all 0. So the diagonals, all other eigenvalues are 0. And of course, they give linearly growing fields. They don't give these sine fields. All right. How am I doing on the time? Okay. So now let's think about a non-minimal geodesic. Gamma t equals e to the I pi n1, e to the I pi n2 n 0. So our non-zero eigenspaces are two-dimensional. I may have some repeats, but that's all right. Two-dimensional eigenspace Eij, and the eigenvalue lambda ij is pi squared over 4 ni minus nj squared. Okay. And the Jacobi equation then on Eij, the Jacobi fields vanishing at the origin are given by a constant times sine of the square root of this thing, which is pi over 2 ni minus nj. Here we'll take ni to be bigger than nj. Okay. So this two-dimensional space is a two-dimensional space of Jacobi fields that vanish at exactly the same places. These vanish at 2 over ni minus nj. And that, of course, is supposed to be less than 1. 2k for k an integer. Okay. So these Jacobi fields are periodic. And the places where they vanish are where this coefficient is an integral multiple of pi, and therefore it has to look like t, sine of t. T has to be of this form. So we want to know how many different points in this, of course, a two-dimensional space, it vanishes at each point because the whole two-dimensional space of eigenvalues is the same sine curve. So I want to know how many points are there like this? Well, these points, 0, which is not going to count. Then I have 2 over ni minus nj, 4 over ni minus nj, up to 2k. Well, ni and nj are both odd. So the last one would be twice ni minus nj over 2 over ni minus nj. But this one's actually equal to 1, so we can't count it. So we have to count how many we have, and how many we have is ni minus nj over 2 minus 1, because I don't get to count the last one. That's the number of points at which these Jacobi fields vanish between 0 and 1. And each one counts with multiplicity 2 since the eigenspace is two-dimensional. So this is nj minus ni minus 2. Now I have to sum up over all ni greater than nj. Okay. So this is the total vanishing of Jacobi fields on 0, 1. That is to say, it's the sum up to but not including 1 of the dimension of the Jacobi fields vanishing at t along this curve. Okay. And therefore, it's the index of the Hessian at gamma of E. Okay. Well, now it's an easy exercise. Well, so first example, if all ni have absolute value 1, then we have to have n plus 1s and n minus 1s. And so this sum is over n squared terms, the n plus 1s bigger than the n minus 1s, but each term contributes 0. Okay. And therefore, because n1 is ni is plus 1 and nj is minus 1. Now there's an easy claim. If not all ni are 1 and summation ni equals 0, then summation over ni greater than nj of ni minus nj minus 2 is greater than or equal to 2 times n plus 1. Okay? And that says, since these sums were the index of the Hessian, the sums over ni greater than nj is the dimension of is the index of the Hessian, that will say at all non-critical geodesics, at all non-minimal geodesics, those are the ones where at least one of these ni is not 1. The dimension, the index is at least 2n plus 1. And the proof, well, it's easy. Suppose, well, for example, all the negative ni are minus 1. Then, since not all the positive ni are minus 1, there exists a positive, let's say nj, those are going to be the smaller one. There exists a positive ni greater than or equal to 3. The number of negative eigenvalues has to be greater than or equal n plus 1. Because if you had exactly n minus 1 eigenvalues, you'd have to have n positive eigenvalues. One of them is at least 3, the others are at least 1, and therefore the positive eigenvalues would add up to more than the negative eigenvalues, which contradicts the special unitary condition. So there will be at least, I mean, the minimum here is to have 1, 3, n minus 2, I guess it is, 1s, and n plus 1 minus 1s. So this adds up to minus quantity n plus 1, and this adds up to plus n plus 1, and there are 2 of them. Okay, so now we have each negative eigenvalue is minus 1. We have this 3. so some of our use that as Ni, and we have 3 plus minus 1, 3 minus minus 1, so 3 plus 1 minus 2 summed over the Nj less than 0. That's a lower bound for the index. But of course, there are at least n plus 1 of these negative ones, and therefore you get at least twice 2n plus 1. The other possibility I have to think about is there exists a +3 or a positive eigenvalue greater than or equal to 3 and a negative Ni less than or equal to -3. Let this be Ni and let this be Nj, and we have Ni times the number of negatives, twice that, plus Nj times twice the number of positives. Because if you have Ni as at least 3, you take any negative eigenvalue, the difference between that negative eigenvalue and Ni will be at least 4. You subtract 2, will contribute at least 2. So that's each of these negative eigenvalues paired with the biggest positive eigenvalue gives at least twice the number of negative eigenvalues. Symmetrically, you get at least twice the number, you get at least twice the number of negative eigenvalues by taking 3 plus 3 is the positive eigenvalue. The negative eigenvalues are at least -1. 3 plus 1 is 4. Subtract 2, you get 2. Similarly, here you get twice the number of positive eigenvalues, but the number of negative eigenvalues plus the number of positive eigenvalues is n. So you get at least 2n. Well, that didn't quite work. I want to get 4n. Oh yeah, but then I have another factor of 2 from the dimension of the eigenspace. So these actually give 4n, which is greater than or equal to twice n plus 1. So that shows the index of non-minimal critical points is greater than or equal to 2 times n plus 1, which is what I wanted. All right, I've got to stop early today. I have a Zoom doctor's appointment. So I have a couple of minutes for questions if there are any. So maybe I should just, once you summarize this way, once you get the general theory set up, it's easy to do this computation in the Lie group, as is often the case. Computing things in Lie groups and local symmetric spaces is quite routine once you have the general machinery set up. So it just came down to a simple computations. Well, this fact about the parallel nature of this curvature operator, and then splitting your Jacobi fields into these one-dimensional spaces, and then just a simple computation using the combinatorics of the unitary group. Not deep at all. But you need the general theory of you start with the Bott-Morse minimal critical points, and then you add these cells corresponding to the bounded below by the dimension of the cell bounded below by the index of the non-minimal critical points. Right. As I say, there's a version for the orthogonal group which proceeds along the same lines, but I'm not going to do it. All right, any questions? You can find all this in Milner's book on Morse theory. All right, I'm going to start next week on the pseudo-isotopy. Cerf's proof that for a high-dimensional simply connected manifold, pseudo-isotopy implies isotopy. So I think of this as one of the great theorems from the second half in topology of the second half of the 20th century. It is a Morse theory proof, as we'll see. So I thought I would finish this set of lectures by showing you that. It's rather complicated. Serif's paper is close to 200 pages, 150 pages. Much of it is very elementary. There are a few beautiful ideas in there. I'll try as best I can to highlight the main ideas, do a few computations along the way, but I won't get too bogged down in them. All right. So see you next week, pseudo-isotopy.